So these are 4 of your TAs. This is Pavitra, that's Jeel, that's Harini, and that's Raghav. You're going to encounter them during office hours. We'll possibly have a different set of TAs in each class, and when they come down, I will introduce them to you. If you encounter them in the corridor, feel free to harass them with ideal questions. But that's what they're here for the rest of the semester. And don't forget to write your names. If you haven't found a pen, there's a pen going around. Now I must figure out how this moves. Wait. No. This is a mystery. How does this clicker move? And what did I do with my glasses? Please settle down. That's nonsense. Something strange. Here. Okay. This is supposed to be moving the slides forward and back, but apparently it's not doing that. All it's doing is how does this strange thing work? What? I'm going around in circles. Ah. Okay. All right, folks. We'll continue where we left off. I'm assuming most of you, all of you must have watched the lecture on Monday. Now, all of you remember the rules for the class. All of your laptops must be shut. So please shut your laptops, every one of you. Laptop shut, 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 shut. You at the back, laptop shut. Please. Do you folks mind shutting your laptops? Thank you. Right. The only time you guys are going to open your laptops or your phones is to answer the polls. They are on Piazza. And when the polls come up, the Piazza threads on which the polls occur are going to be shown on the slide. So how many of you have watched the lecture from Monday? And some of you haven't, right? Those of you who haven't are going to have some trouble following this, okay? So here's where we ended up on Monday. We showed that the business of training a neural network was one of empirical risk minimization. You are given a training set of input-output pairs. So each training instance is an X and a D. What was the D over here? Young men, what was the D? That was the desired output. Thank you, Anshi, right? So the way we specified it was that the chalk here, supposedly, lovely. So the network itself would be modeling some function. The actual function you want might be something else. And what was it you wanted to minimize when you trained the network? The error. How did we define the error? The area of this gap. This is what we wanted to minimize. Could we actually minimize it explicitly? Why not? You don't know the entire function. And so how did we deal with this? This is your input, X, and this is the function, right? Function and desired value. So how did we deal with it? We We took samples. And so this is my target function. This is my D, right? And so you took samples, various samples, and each X is a sample, and the D is the desired value of the sample at that X. So we had a collection of those. And then what was this loss function that I defined? What was the loss? The approximation of what? The area. And how did we approximate it? Lakshay, how did we approximate it? How did we approximate? So what was the loss supposed to be? What was the loss supposed to be? What did you really want it to be? So the loss was actually supposed to represent this shaded area. That's what you're trying to minimize, right? But what is it exactly? Jadev, go ahead. No, but the function that I've written on the slide, what is that? So that is simply the average of these lengths, right? At the training samples. And our expectation was that if you minimize the average length, the entire area would decrease, right? Which is a reasonable expectation. That's why we're going to be optimizing it. So the loss is a proxy for what we are trying to minimize. What is the loss a function of? Once I give you the excess, what is the only thing I can modify to decrease the loss? The parameters, right? So if I change the parameters, these x's stay the same, but the function is going to move up and down, and that is your loss. And we are going to be training our network to minimize this loss. Any questions? Anybody, right? Okay. And so this is an instance of function minimization. What is this a function of now? The loss. What is it a function of? Okay, parameters, the parameters, right? So and so we are trying to minimize this with respect to the parameters. This is a instance of function minimization. So we're going to be spending a few minutes talking about function optimization. I am giving you a generic function, some f of x. How do I find the value of x at which the function is optimal, either minimum or maximum, depending on how you think about it. We are going to be speaking of minima, right? So first, if I give you a function f of x, how do you understand the derivative of the function with respect to x? What does it mean according to you? Speak up, Nivedita. The slope? Katrina, how would you define it?
The difference, the slope of the line.
The slope of the line is a good thing. It's basically the derivative of the function at any point basically tells us how much a minute increment of the argument of the function will change the value of the function. Now, it's not convenient to think about it in terms of slope, as we will see in a slide. But if I'm at this x, if I perturb my x by a tiny bit, that's going to result in a small perturbation of y. And so the derivative is going to tell you how much an increment in x, not any odd perturbation, how much an increment in x modifies y. And so the way we define the derivative is the multiplicative factor that multiplies this increment, a tiny increment delta x, to give you the corresponding delta y. How have you seen derivatives written in class typically? When you've done your math courses, how do they write derivatives? Would that always work? When would it not work? No, but can I write it as dy over dx always? What if y is a function of multiplication? What if x is a vector? Then can I write dy over dx? I cannot write dy over dx. It's not a useful notation, right? And so that's it. So the way to think about the derivative always is this multiplicative factor that multiplies you mind shutting your laptop? Okay, fine. But take it on paper if you can or something. So anyway, so it's a multiplicative term that multiplies a small increment delta x to give you the corresponding delta y, right? And when x and y are scalar, then and only then, because y could be a vector, x could be a vector, right? When x and y are scalar, then and only then can you write this as dy over dx. But if y equals f of x, the better notation is f prime of x. Why would I say that? Anyone? Why is f prime of x a better notation? Is the derivative the same at every x? Yes or no? So does dy over dx indicate this fact? No. When I say f prime of x, it is explicitly indicative of the fact that this derivative depends on the location x. Everybody with me? Right. So the derivative is actually giving you the rate of change of the function of x, how much the function increases when you increase x a tiny bit. So over here at these places, increasing x increases the function y, increases y. So would the derivative be positive or negative? Can I hear that? Positive. And if out here, what would the derivative be? Where increasing x decreases y? Negative, right? These are things we're going to be working off all the time. So now, if I'm speaking of a multivariate function, it's a function of many variables. So y is f of x, but now x, according to me, is a column vector, right? So if x is a column vector, then what would an increment delta x be? X is a vector with many components. What's an increment delta x going to be? What kind of vector? A column vector of the same shape and size as x, right? Because I'm just a small perturbation of x. And so I have delta x also be a column vector. Now, again, if I think of the derivative is still going to follow the same rule. If this is a multivariate function, x is 2 dimensions in this example, in this pictorial example, and y has some scalar value, right? And so at any x, I can perturb x by a small amount. And correspondingly, y is going to get perturbed as well, right? And so if I change x by a tiny amount, how much does y change by? I can still write that like so, right? Delta y is a multiplicative term that multiplies delta x. And that alpha over there, that is the derivative. Now, what is delta x? X is a column vector. So what's delta x? Is it a row vector or a column vector? Okay, so what will alpha be? Alpha must be a row vector, right? Otherwise, you cannot multiply the two and because delta y is a scalar. The left-hand side is a scalar. Therefore, the right-hand side must be the product of a row vector and a column vector, right? And so so alpha is going to be a row vector, and delta y is going to be alpha 1 times delta x1 plus alpha 2 times delta x2, and so on. And now what this is telling us is that this delta x can be in any direction. It doesn't matter which way. So it's a multivariate function, right? So if I'm at any location, I can take a step this way, I can take a step this way, I can take a step back, I can take a step in any given direction. And that equation is always going to hold. Regardless of the direction in which I'm taking a step, delta y is going to be alpha times delta x, right? Now, when I take a step, I can choose to take a step along an axis so that only x1 changes, but the x2 through x3, x2 through xn do not change. In that case, do alpha through 2 through alpha n matter? No, because the corresponding delta x's are 0. The rule still holds, right? And so in that case, the increment that you're going to get, so the partial derivative is defined as the ratio that multiplies delta x1 to give you delta y when the rest of the x's do not change. Each partial derivative tells you how much the output changes when only that variable is perturbed and no other variable is modified. And so I can write it as notation like, so I'm going to use this inverted triangle frequently, which is the inverted triangle delta x, y delta x, which is the derivative of y with respect to x. And it's going to be a row vector of partial derivatives, right? Now, how many of you have heard the term gradient? So how do you understand the term gradient? The gradient is the transpose of this partial derivative vector. And the gradient is going to have the same shape as x. The derivative is the transpose of x. The gradient will have the same shape as x, at least in the notation that we're using. It's a fairly standard notation, right? And so I can just write this as the gradient is the transpose of the derivative, a column vector of the same dimensionality of x. Now, what is the gradient? So we've all heard this term gradient, right? What does this vector of partial derivatives mean? What is it? It's a derivative, we know that, right? But what is that vector of partial derivatives? Does anybody know what the gradient represents?
Change in all the dimensions.
Change in all the dimensions.
Change required to minimize the error.
In the direction of the steepest.
It's the direction of the steepest ascent, right? And let's see how that works out. Thank you, Quentin. So this term is a vector in a product, right? It's the product of a row vector and a column vector. That's a vector in a product. And what do we know? What is a vector in a product? If I take the inner product of two vectors, what does it quantify besides the length of the vectors? Distance. The angle between the two, right? So when I look at two vectors, I'm looking at the inner product of the red and the blue vector over here. Both of them are the same length. And I'm changing the angle between the two. The vector inner product is length of one vector times length of the other vector times cosine, right? And so as the blue vector goes around, the picture to the right shows you the value of the inner product. It's a sinusoid. When does it peak? In which direction must the blue vector be for this to be the largest? When the angle is 0, when the blue vector is pointing in the same direction as the red vector, right? And so if we go back to our problem, we said df is the derivative, which is, effectively the transpose of the gradient, times dx, right? This derivative is given to you. That's a fixed vector. The only thing that you can change is dx. Suppose I fix the length of the step I take. If I take steps in different directions, which direction will give me the greatest increase in y? Yes, Stella?
Same direction.
Anybody else? Nicole, which direction will give me the greatest increase in y? Back there. Yes, you're the only Nicole I see.
Sorry, can you repeat the question?
So the derivative of the function with respect to x is fixed, right? So the only thing I can change is the direction in which I step. Again, the derivative was defined as how much the function value changes by when you change the input by a small amount, right? So if I give you the derivative at some point, now if it's a multivariate input, I can step in any direction. I can go left, I can go at 30 degrees, I can go up front, I can go back. There are many directions in which I could take a step. In which direction should I step for the corresponding increase in the function value to be the largest?
The direction of the gradient.
Why? Wang at the back. Why? You there? Yeah. So why should the direction in which I move be the same as the direction of the gradient for the largest increase in y? Guys, it's 3 minutes into class, I've lost 80% of you. So I know it's 8 in the morning, pay attention, right? So what was this, right? That term over there. We just said this is a certain kind of operation. X is a vector, right? Is the derivative a vector, right? Yes or no? Can somebody help him? Is the derivative a vector? Yes, okay. So what is the product between the two? What is the product between the two? Prachiti.
The product of the distance times cost.
It is the inner product or product between the derivative and this vector, right? When is it largest? When they are in the same direction, which means dx must be in the same direction as the derivative for the function to increase the fastest. You guys at the back, Ibrahim, does it make sense? Right? Please be alert, right? And so the gradient is the direction of the fastest increase of f of x. So which means that of all the infinite directions that I can step in over here, the gradient shown by the black arrow is that is the direction which is the vector of partial derivatives. If you take a step along that direction, that's when the function is going to increase fastest. When will the function decrease fastest? When you walk in the opposite direction, right? This is okay. And there are locations where the derivative is 0. That's where the function is flat. Okay. There's another property of the gradient. This is a function. If I slice it, then you're going to get an equal level, equal height contour, an edge, right? Imagine a bowl. I slice it. You're going to get these edges. Those edges are all at the same height. And if you look at the shadows on the ground, there's going to be a curve. And that's the level set. The gradient is always going to be orthogonal to the level set. Questions? Yeah.
Could you repeat why it's f of x transpose? Like why is the gradient f of x transpose?
The gradient is defined as the same dimensionality as the derivative, as the vector. And we know that the derivative is?
So derivative is a row vector.
The derivative is a row vector. So you'd have
X is a
column vector. That's it, right? So, okay. There's also this other term, which is the vector matrix of second derivatives called the Hessian. I'm not going to spend time on it, okay? So here's a poll. There are two questions on Piazza. Please respond to them quickly. We are 15 minutes into class. We should have been 5 minutes into class. Can you run the timer? Okay, guys, time's up. All right. Where's my trident? Anybody want to answer these questions? In the first poll, at any location x, there may be many directions in which we can step such that the function f of x increases. True or false?
True.
Can everybody say true together, please? Thank you, right? Including the folks at the back. So, Wong, are you working on the poll? If not, can you shut the laptop? Thank you, right? The direction of the gradient is the direction in which the function increases fastest. True or false?
True.
Right? The gradient is the derivative of f of x with respect to x.
True.
Is it true? Okay, why is it false? It's a transpose of the derivative, right? If y equals f of x is a scalar function of an n cross 1 column vector variable, x, what is the shape of the derivative of y with respect to x? If the vector is n cross 1 and y is a vector scalar, what is the shape of the derivative of y with respect to x? Can you say that aloud? 1 cross n, right? Because it has to multiply the increment in order to give you delta y, right? And so now let's go back to the function here. You go.
I have one question.
Yeah.
About the two one question. What is the point is on the plane or on the hill, how can we guarantee that at any location we can find the point, we can find the direction that fx is?
If you're on the flat region, the f of x is not increasing in any direction, so the derivative will be 0. Right? Okay. So now the problem of optimization, in our case, if you're looking at minimization, is you have some function of a variable. We are trying to find the value of the function where the value of the variable where the function is minimum. So in the scalar case, you're trying to find the location pointed by the red arrow. Here, you're trying to find the location of the blue dot. How did you do it in school? If I gave you a function, how did you find the value of x where the function was minimum? You differentiate it and then equate the derivative to 0. That's because the assumption is that at the minimum, the function is, the derivative is 0. This is how we did it, right? Is that really a minimum though? What other test must be run? The second derivative, because, okay, here's a poll. Answer this for me. Okay, I'll give you 10 seconds, guys. I'm running out of time. Okay, time's up. What's the answer? The second derivative must be 0. Does that always work? The second derivative must be positive, but that's not a sufficient test, as we will see later, right? But this is what you learned in school. So what happens is that both maxima and minima have 0 derivative. They are what are called turning points. The function turns at these places. So at the maximum, the first derivative goes from being positive to being negative. So if you plotted the first derivative, it's going to go downwards from being positive to a negative. At a minimum, the first derivative, the slope goes from being negative to positive. So if you plotted the slope, it's going to be going upwards. And so if you took a second derivative, which is the derivative of the slope, you're finding that at the maximum, the derivative of the slope is negative. At a minimum, the derivative of the slope is positive. So you look at the second derivative. And so the way you would solve for the minimum is to find out where the function derivative is 0 and the second derivative is positive, right? And so this was the standard solution that we have done in high school. Now, the problem is that a derivative can go to 0 at various places. You can go to 0 at inflection points. An inflection point, you can go to 0 at maxima, at minima. At inflection point, an inflection point is a point where the function is going down and then sort of pauses for a bit and then continues going down. So if you plot the derivative, it's negative, goes to 0, goes back to being negative. Or maybe it's rising, then pauses a bit and rises again. So these are places where the derivative is 0, but the function is neither a maximum nor a minimum. So, and for functions of multiple variables, it gets a little more complex. So here's what we find for functions of multiple variables. The optimum is still likely to be a turning point. But then here, those are the places where the gradient is 0. So it doesn't matter which direction you take a tiny, tiny, tiny step in, the function value doesn't change. But if you want to find the value of the input where the function is minimum, you can just write out the equation for the gradient, equate it to 0. But then once again, this is no longer sufficient, right? Because you have to look at the second derivative. And in the case of the second derivative, something crazy happens. We introduce the term Hessian. I'm not going to define what the Hessian is here, but it's just a describe it. It's a matrix of second derivatives. Now, if you look at a function of this kind, look at, let me go to the previous slide. So a function of this kind has, what happened? It's a function of 2 variables, right? In this particular example. In general, you can have a function of many variables. So think of a bowl. A bowl can have a shape of this kind, where maybe if you have a saddle, So there are different kinds of bowls. I can draw a bowl, which is like so, right? And then regardless of whether I slice it along this axis or this axis, the bowl is always going down, right? Now, what if I have a function of this kind? So this is like a boat. I'm really bad at drawing, but think of a boat that's bent down, right? At this location, if I slice it along the x-axis, is it going to be a minimum or a maximum? If I have a boat that's bent down, so you have a sheet of paper. So thank you, Ansh. But you know, if this one were a curved board, except it's folded down like so, right? So it's a curve. Now, then up here, so this is what it looks like. Let me try to draw this, right? And this is what the surface looks like. Okay? You get the idea. So out here, if I slice it into the wall, along that slice, am I going to find a minimum or a maximum? I'm going to find a minimum, right? But if I slice it in this direction, am I going to find a minimum or a maximum? So there are two directions, and the behavior along the two directions are very different. In one direction, the second derivative is going to be? Is it going to be positive or negative? And what about the other direction? Negative, because it's maximum in one. So that's what the Hessian tells you. The eigenvectors of the Hessian tell you these directions, primary directions, and the eigenvalues give you the curvature along these directions. If you have a strict minimum, every single eigenvalue of the Hessian is going to be at a minimum. Yeah, every single eigenvalue, the curvatures along all the different directions, they're all going to be positive, right? Everybody get that it's going to be positive? Yeah, the lady at the back, can you shut your laptop? The rules are for through the class. You there? Yes. Do you mind shutting the laptop? Okay. It's very hard for me to keep track, right? So I make an exception for one person. I have to do it for everybody. I apologize. But so maybe use a notepad or something. And so if you have a strict minimum, it's going to look like a bowl. Every second derivative is going to be positive. Whereas if you have something like the peak of that bowl, it's going to be, some are going to be positive and some are going to be negative. And so if you want to find out if you've got a minimum for a complex function, compute where the derivative goes to 0, compute the Hessian at the candidate solution, and verify that, that all of the eigenvalues are positive, which is the only condition under which it's a minimum. And that becomes much harder for multivariate functions. And then if you've got functions of this kind which are really ugly, you can't simply even solve for the derivative and say the derivative has gone to 0 at this point. That's hard. And so then we have to take iterative solutions. You're going to start at some point and check, is this a minimum or not? And one way to check if it's a minimum is to look at the derivative. If it's not, then you take a step. And then you check, is this a minimum? Then you take another step. And you keep doing this till you think it's a minimum. In which direction would you want to take a step if you're doing this? You want to take a step where the function is decreasing, right? And so this is in single dimensions. You're going to start at some point, and then you'll check, is the derivative positive? If the derivative is positive, what will happen if I move forward? Will the function increase or decrease? So must I move forward or back? Go backwards, right? If the derivative is negative, will the function decrease or increase if I go forward? Decrease. So should I go forward or back? Go forward, right? So simple. So you're going to, at each point, you're going to check if while the derivative is not 0, if the derivative of this function is positive, you're going to take a step back. If the derivative of the function is negative, you're going to take a step forward. Everybody with me? And then can I collapse those two into a single rule? Yeah. Instead of having an if, how?
Use the direction of the gradient to pick this.
Yeah, but without an if clause. Can I write a single formula for this? Yeah.
Just subtract the gradient.
So what I can do is to multiply, wait. This thing is doing strange stuff. So I can just multiply the step by the sign of the derivative, right? And so if the sign of the derivative is positive, I'm naturally taking a step back. If the sign of the derivative is negative, I'm naturally taking a step forward, correct? Or I can group the two, and I just say I'm going to take a step against the derivative. Easy enough, right? This is a function of a single variable. And if you keep doing this, eventually you're going to get at the minimum. So here's your third one. Yes. These watches are cool. Done. Okay, guys, time's up. Anybody want to answer this question? At any location x, there may be many directions in which we can step such that f of x increases. Is that true? Yes or no, guys? Because if the function is increasing, if I've got a hill, I can go forward and I'm going to go up. But even if I go up at an angle, I'm still going to be going up, right? So there are many directions where the function can increase. The direction of the gradient is the direction in which the function increases fastest, right? Also true. And the gradient, well, that's a repeat question, so let's go back. Okay, so in the multivariate function, we know that moving in the direction of the gradient is where the function increases fastest. Moving exactly opposite the gradient is when the function decreases fastest. And so, Rohan, what's a reasonable rule to be following now? If I'm optimizing the function, how do I do it? Pay attention, right? So in a when I'm trying to optimize a multivariate function, what is the rule that I must follow to decrease the function each time I take a step? Which direction must I walk?
Opposite to the gradient.
Opposite to the gradient, right? Because and why is that?
Because gradient is the direction in the function increases. So like you need to go.
Exactly. You want to go in the direction of the steepest descent, right? So, and that's what the rule is going to look like. To find a minimum, you always move exactly opposite the direction of the gradient. So if I'm trying to minimize my function with respect to x, I say xk plus 1 equals xk minus some step size times the gradient. And that's my gradient descent rule. When do I stop? I can stop when the derivative is 0, right? I can also stop when the difference between the value of the function at adjacent steps becomes really small. So that's basically what I do. This is the overall gradient descent algorithm. You initialize your x, your initial step. And then at each point, you compute the gradient and you take a step against the gradient, and you keep doing this until the function does not decrease very much anymore. Everybody with me? Right, yeah.
But isn't there a chance of people that get stuck in the local minimum?
We're not speaking of local minimum. Yes, this is a way of finding a local minimum. You need a name tag. Okay. So now, when I do this, I have two kinds of shapes over here. In the first shapes, the function that I'm minimizing is a nice bowl, right? So far away from the minimum, the slope is steep. Close to the minimum, the slope is small. Far away from the minimum, do I want to be taking big steps or small steps? At the minimum, small steps, right? What will the derivative be like far away from the minimum? It's going to be large. Close to the minimum, small. So for functions like these, if the step size, the learning rate that you multiply the derivative with is constant, it is going to work just fine. It's going to take you carefully to the minimum. On the other hand, if I have a function like the crazy one down there, would that rule work? Not necessarily, right? You want functions of the kind that we have in the upper picture because those are the nicest ones. And anyway, my fourth and last poll before I begin speeding up through the rest of the lecture. I think the second and the fourth options are identical. There's a mistake. Anyway. Yeah. Okay, easy. Does anybody? Yes, Ibrahim.
Just have something I wanted to say. I don't know if I'm the only one, but I was not able in previous polls to choose multiple answers in the application.
That might be a bug. We'll fix that, right? Thank you. So guys, are there any questions on Piazza or on Zoom? Okay. So what's the answer here? Opposite the direction of f of x, right? Now let's return to our problem, which is this guy, which is, here is the problem we had again. We were trying to minimize loss function, which is a function of the weights. And we are trying to minimize the loss function with respect to the weights. So what is the mechanism we'd use? The negative gradient. You're going to be using a gradient descent rule. Do you mind shutting the laptop if you're not taking notes? Yes, thank you. So that's the same rule we're going to use. We'd initialize our weights. At each point, you're going to take compute the gradient of the loss function with respect to the weights and take a step against it, right? But to do this, we need to set the problem up. Everything needs to be specified, right? Now, I'm given some training data, x's and the corresponding target d's. I have to define a loss function, which is an average of the divergences at all of my training samples. And I have to minimize this with respect to w. What are the things I don't know? I don't know what these d's and x's and d's are. I have to specify them, right? I don't know what this function f is. What is my network? What is my divergence, right? And unless I specify all of these, I do not have my function. I cannot minimize it. So let's start with this function f. What is f and what are its parameters w? From our, yes?
Question on Zoom. Can you add some randomness in search to back out of local minimum?
We'll talk about those in the coming lectures. Yes, that's a good question. And the answer is yes, and that's in fact something that we do. In fact, there's a lot of work on how we can not get stuck in bad minima, and we'll deal with it. So our network is going to be of this kind. It's going to be a multi-layer perceptron. Every kind of network that you'll deal with is eventually going to be an MLP. It's a directed network. You have inputs and you have outputs, and information always flows from the input layer. The set of inputs is called an input layer for whatever reason. And then those inputs are going to be operated on by the next layer of neurons. Their outputs are going to be operated on by the next layer of neurons all the way until the output. Information will not be flowing back. So no neuron is going to see the same input twice because it's gone out ahead and come back. That is the kind of network we're going to be dealing with, right? So you have input layers, output layers. The intermediate layers are hidden layers. The individual neurons are going to be our favorite perceptron. The perceptron first computes an affine function of its inputs and then puts it through an activation function. And again, what was the difference between affine and linear, guys? Remember? Offset, right? And what kind of activation function did we like? We wanted continuous graded things, which told you how far away you were from any boundary. Otherwise, it would gate information, right? So those are the ones we would typically choose. So in general, you can think of, instead of saying a function of an affine value, you can think of any continuous differentiable function of the inputs. But the activation applied to an affine value is the one that's most popular. That's what we'll be considering, right? We are assuming this unless otherwise specified. The parameters are the weights and the bias. And so here are some activation functions that we typically use. The threshold activation is a horrible activation function, so we're almost never going to use it. But then the threshold activation looks like so, right? The sigmoid is a smooth version of the threshold activation. What will its derivative look like? What's its derivative going to look like? It's going to be the derivative. If I chose this, do I have a different color? I don't know if I do. It would be nice if I did. I could draw those. They're all yellow. Okay. So the derivative is 0 out here. The derivative is also 0 out here, right? And then it increases to a maximum and then decreases again. And this derivative over here is going to be, the peak derivative is 0.5 for a sigmoid. A tan H is like a sigmoid, but instead of going from 0 to 1, it goes from -1 to 1. And so a tan H is going to be like this, right? What will its derivative be like? The derivative is again going to be 0 out here, 0 out here. It's going to peak and come back, but at this point, the derivative is going to be 1.0. The difference between the sigmoid and the tan H. And so larger derivatives are good, which is why we often use tan H activations instead of sigmoids. Now, the other kind of activation we like to use is the rectified linear unit, which is basically a rectification function. If this is x, 0, the function is going to be like this. What is it? What does its derivative look like? It's going to be a 0. The derivative will be 0 till here. And then from here, it's going to be 1, right? That is the derivative. So the derivative is now discontinuous, right? What would be a nicer function than that? If the derivative itself was smoother, that would be a nicer function, right? So if I make the derivative like so, instead of the step function, then what will the actual function look like? It's going to look like this, right? That's the soft plus. These are all very popular activation functions. Anyway, so you have the sigmoid, you have the tan H, you have the rectification function whose derivative is a threshold function, and then you have the soft plus whose derivative is a sigmoid. So, and various others, right? You can also have what are called vector activations. Now, if I look at any layer of neurons, they have a specific characteristic. If I have a layer of neurons over here in the network, each neuron has, all of these inputs come here. There's a Z that's computed. First, you compute an affine term, right? And then this is put through the activation and you get an output. So this happens at every one of the neurons. If I modify this Z, will it change this output? Anybody? Can everybody say no or yes together? If I modify the first Z, will it change the second output? No or yes? No. Okay, so these are what I call scalar activations. Each one operates locally, right? I can have a different kind of activation, which I call a vector activation, where if I modify this Z, all of these guys will change, right? And so those are what we call vector activations. So in those cases, and the most common one is the softmax, where you exponentiate each of the Z's and then normalize them so that they sum to 1. So the result is that the outputs are all positive and they sum to 1. They look like a probability distribution. So we try to use them as probability distributions. And so this has an interesting behavior from our perspective. And that is that in these neurons, if I change this weight, then changing this weight is only going to change the output of this neuron, right? Whereas out here, if I change this weight, changing this weight changes the Z, but that's going to change all of the Y's. And so if I look at the derivative of this output with respect to this weight, what is it going to be in this case? Is it going to be 0 or non-zero? So if I'm trying to find out what is the derivative of this output with respect to the output of this connection, the weight of this connection, what will it be? Because modifying it doesn't change that other output, right? Whereas if in the softmax case, changing any weight is going to change all the outputs. So all the derivatives are going to be non-zero. That makes sense to everybody? So, and in fact, you can think of every layer as a vector activation where there is no interaction. Like you can think, a special case, right? So we've defined the function f, and its parameters w are the parameters of the weights and biases of the neurons, right? What are these input-output pairs? Let's define them next. So we are given a training set of input-output pairs, which means you have several instances. Each instance comprises an x and a corresponding d. And so the x is going to be a many-component vector. And if the network has many outputs, if the network is outputting a vector also, d is going to be a many-component vector as well. And so each training input is going to have several components. Then you have several training instances. I'm going to drop the subscript that distinguishes between different instances. I will focus on just one instance, right? So each training instance has several components. The desired output is going to have several components. And then if my desired output has 10 components, how many outputs must the network have? Guys, my network, I want a function, I want the desired output in response to any input is a 10 component vector. How many outputs must the network have? 10, right? Just as many as the number of outputs I need, okay? And so let's see how we would represent the inputs and the outputs. The input is just a vector of numbers. In fact, if the input is a scalar, it can just be a scalar, right? So if I'm looking at images, the input is going to be a vector of pixel values. If I'm looking at speech, the input is going to be a vector of speech features. If I'm looking at text has to be converted to a vector of numbers, but we'll convert that to a vector of numbers, right? And you can have other real valued stuff. Now, some of you are falling asleep. I know it's very early in the morning. Do you want a 5-minute break to go wash your face or something? Anyone? I know it's tough. 8 o'clock is tough on me. It's going to be tougher on you, your kids. So anyway, if my desired output is a scalar, if it's real value, no big deal, right? My network will have just one output, and it's going to be a real valued output. If my desired output is a real valued vector, no big deal. I'm going to have as many components as my network as the number of components in my desired output, and that just works. It's going to be outputting numbers. On the other hand, if I'm performing classification, then the desired output, if I'm performing one class classification, the desired output is binary, right? I see a picture and I have to say, this is a cat. No, this is not a cat. I want a 1 or a 0 to be output, right? So in that case, my network is going to have just one output in most cases, right? This is a cat, and it's going to output a 1 or a 0. And the desired output D is going to be either 1 or 0, right? What about the actual network itself? For the actual network, in this case, we will use a sigmoid activation at the output neuron. The sigmoid activation is this activation which goes smoothly from 0 to 1, as we saw. And we can think of the output of the sigmoid as the probability of the target class. So it's not saying this is a cat, this is not a cat. It's giving you a value between 0 and 1. And you can think of that value as the probability of this being a cat. And we will see in later classes why this makes complete sense, right? Then how about a multi-class case? If I'm trying to perform classification, and I'm trying to distinguish between, say, cats, dogs, camels, hats, and flowers. Now, these classes are abstract entities, right? A cat is not a number. A flower is not a number. How do I convert these to numbers? So I'm going to arrange all of my classes according to some canonical order. In this case, dog, cat, dog, camel, hat, and flower, right? And then to represent the class cat, I'm going to construct a vector which has as many components as the number of classes I have, where there is a 1 corresponding to the class that I'm trying to represent and 0 elsewhere. So a cat will be a 1 followed by 4 zeros because a cat is in the first position. A dog is going to be a 1 in the second position. The rest of the components will be zeros. A camel is going to have a 1 in the third position. The rest of the components are zeros. This is called a one hot vector. It's one hot because only one of the elements is hot. It's one. The rest of the elements are cold. They're all 0. This makes sense to everybody? Everybody with me so far? Okay. So in this case, the desired output D is also going to be a multi-component vector with as many components as the number of classes, right? Now let's go back. Ideally, if I'm giving you a picture of a cat, what would the ideal output here of the network be in this example? A 1 in the first position and everything else must be zeros, right? And so, and that's what you want the network to ideally output. The network must ideally output a one hot vector. More realistically, it's going to output a probability vector. It's going to output the probabilities for all of the classes. What kind of activation gave you something that looked like a probability vector? Softmax, right? It gave you a bunch of outputs which summed to 1 and they were all positive, right? And so in this case, we are typically going to be using a softmax activation at the output, which just, again, exponentiates the affine term and then normalizes it. The exponentiation ensures that it's always positive, and the normalization ensures that they all sum to 1. You could use other functions that you devise similarly, but this thing has some very nice properties. You just want to make sure that the outputs are positive and they sum to 1. So they all lie between 0 and 1 and sum to 1. And now they will substitute for the probabilities of the classes. And so you would actually get the probabilities for each of the classes and compare that to make your decision based on it. Yes, Vibha?
I had a question. So you said for binary classification, it's typically the this or not this.
Yes.
So that in that sense, if you had two classes only, would you use two neurons in the output or would you use just one? For example,
You could do either, really. And so using 2 neurons is exactly the same as using just one mathematically. But yeah. So, and we can take it off and I'll show you how the two are the same. So if I'm trying to set up a training problem, you'd be given a bunch of training instances, e.g. images of digits, along with information about which digit it represents. And then if you're performing binary classification, like is this a 2 or a not, that you'd be performing one kind of training. If you're performing multi-class classification, which digit is this? You're going to look at it somewhat differently. So for binary classification, that's the kind of training data you're going to provide. You're trying to build a network to determine if this digit is 2 or not. So along with each image, you'd have a binary label, which is either 0 or 1. 0 means it's not 2, 1 means it is 2. And the network is going to have a single output with a sigmoid activation. Whereas if you're doing a multi-class classification, then corresponding to each digit, each image, you're going to have the label for the digit. And the label for the digit is going to be, in this case, it's just a number, but then you would have to convert it to some format for actually training the network. What was that format? One hot, right? And so your network itself would have as many outputs as the number of classes. So we have defined F, we have defined X and D. There's one last term to define, which is this divergence. Now going back to the last class, what was the property that we desired for the divergence? What was it? What important property did the divergence have? It had to be differentiable, right? You wanted to know how much changing the output of the network a little bit changed the divergence. If you cannot compute this, then you won't know, you won't get any signals on how to modify the network parameters to decrease your loss, right? And so the first thing is that for the loss to be differentiable, the divergence must be differentiable. If it's not differentiable, you're not going to be able to do anything. We went into this at some length on Monday, right? So what are these divergence functions like? If I'm trying to make real valued predictions, so I'm trying to predict maybe the values of all the stock indices tomorrow. These are real valued predictions. This is not a classification task, right? And then when I'm training the network, I'd actually have the real values. So the D's are going to be the actual values I want the network to output. The network is going to output a bunch of values. And so the network outputs a vector to the desired vector. And a very nice loss over here is the L2 divergence, which is half of the squared Euclidean distance between these two vectors. Now, if you wonder why we have a half, the half is, it's not important, but it's very useful to have. So we always define it with a half. And that is because when I take a derivative of this squared Euclidean error distance, the derivative will get a 2 out of it. And the 2 and the half will cancel out, right? And so here is the beautiful thing. As a result, the derivative of the divergence with respect to the output of the network ends up simply being y minus d, which is the error between the actual output of the network and the output and the desired output of the network. Now, you might say, the norm of d minus y and the norm of y minus d are the same, correct? So how do I know what the sign is? Should it be minus of y minus d or should it be y minus d? How do you define this? How do you think it's y minus d?
As in from the definition of derivative or just
From the do it either way.
from the definition of the derivative, you just multiply the 2 times 1.
Yeah, but then I could have written it as y minus d whole squared as well.
No, then you will have to multiply it by a negative sign because you're finding it with respect.
So she's giving me the correct answer mechanically speaking, but think of it this way, right? If y is lesser than d, then will increasing y decrease the error or increase it? Y is lesser than d. So will increasing y decrease or increase the error? Decrease the error. So what will the derivative be? If y is lesser than d, then the derivative must be increasing y decreases the error. What will the derivative be? Negative, right? Y minus d has the negative sign because y is less than d, right? If y is greater than d, will increasing y decrease the error or increase it? Increase it. What will the derivative be? Positive. Does this match? Right? This is a simple check. Don't go with math. You're going to get your math all tangled up every single time. Just look at it from what it is supposed to be doing. That's a very important thing to be doing anytime you're talking about derivatives and such like. Because the intuition is sitting there and staring you in the face if you're only willing to think about it. Make sense to everybody? Right. So now, if I'm performing classification, then we like to use a different kind of divergence, the Kullback-Leibler divergence. Now, if I'm performing a binary classification, is this a cat or not, right? Then the output is going to be the probability of a cat. Y is going to be some number between 0 and 1. The desired output is going to be either a 1 or a 0. It's 1 if it's a cat, 0 if it's not a cat, right? So in this case, here's the thing. I can think of my one-hot vector as an extreme case of a probability vector, can I not? It's a probability where most things have probability of 0, and one of them has a probability of 1. So now I have two probability vectors, and the Kullback-Leibler divergence actually quantifies the difference between two probability vectors. It's defined like so. It's d is going to be either 0 or 1. It's minus d log y, minus of 1 minus d log of 1 minus y. Now what happens when the desired output is cat? If the desired output is cat, d is 1, right? Which term remains? First one. It's going to be d log y, right? Now should it be d log y or minus d log y? Y minus. Y minus. Yeah.
So log value implies a probability value between 0 and 1. Logarithm of it will be negative.
And then, so the negative and negative will cancel out. Another property we had for divergences was that they must always be positive, right? And so when is this going to be the smallest? When is this going to be the smallest, Bruno? Yeah, so in this particular case, I'm asking you, right? So I have d is 1, When is this going to be the smallest? Will it be the smallest when y is 0?
No.
That's the divergence. When will it be minimized? At what value of y will this be smallest?
So I'm having some trouble with the intuition here.
So skip the log for now, right? So this is how it is defined. Assuming this is how it is defined, if you'll bear with me for 5 minutes, we'll get to the log bit too, right? So if my desired output is 1, when is the smallest?
When it's 1.
Look at that and tell me.
Are we looking at the part of this thing that says derivative, or
Just the divergence. When the desired output is 1, when is the smallest? Maybe Jacob, you can tell me. When y equals 1, right? If d is 1 and y is 1, log of y is 0. And the smallest value for the divergence is always 0. So this minimizes when y is 1. When the desired output is 0, then what happens? Which term remains, Bruno? There are 2 terms here. The second term, because the d goes away. And when is that minimum? When y is 0, because 1 minus 0 becomes 1, log of 1 is 0, right? So it has this nice property that this is minimum only when the desired output is exactly equal to the target, the actual output is exactly equal to the desired output, and it's positive otherwise. Now, the derivative of this divergence with respect to y has an interesting property, right? If the desired output is 1 and y is less than 1, should I be increasing y or decreasing y to reduce the error? Increasing y, right? So increasing y will reduce the error, right? And so what is the sign of the derivative? Negative, right? So you can see that minus 1 over y is always going to be negative because y is always a positive number when the desired output is 1, right? When the desired output is 0, will increasing y increase or decrease the error? If the desired output is 0, right? If I increase y, what happens to the error? It increases. What will the derivative be? Positive, right? So you can see the second term. Y is always a positive number. 1 minus y is a positive number. 1 over 1 minus y is positive. The derivative is always positive when the desired output is 0. The derivative is always negative when the desired output is 1. That makes sense to all of you guys? Right? Okay, so it has this nice property. Now, if I go for, so L2 versus log. Now, even for the classification case problem, right, I could compute an L2 error between the network output and the desired output. This crazy business of the log, Bruno couldn't figure out what the log was doing, right? Why not just use an L2 error? Look at what's happening over here. The red curve shows the L2 error. The blue curve shows the Kullback-Leibler divergence. The first plot is when the desired output is 0. The second plot is when the desired output is 1. So let's focus on the plot on the left just for intuition. When is it smallest? When is the divergence smallest? When y is exactly equal to 0. So in both cases, regardless of whether it's L2 or it's KL, the divergence is minimized when the actual output of the network matches the desired output, right? But then the output, if your desired output is 0, you want to say this is not a cat. And the network says, I'm absolutely certain this is a cat. How wrong is the network? Is it just somewhat wrong or infinitely wrong? Infinitely wrong, right? So what does the KL divergence tell you? It's infinitely wrong, correct? What does the L2 error tell you? It's kind of wrong, right? Yeah, I know. This, maybe a cat, right? That doesn't make sense. And so the KL divergence has this property that when you're very wrong, it forces your output to change very fast in order to fix the error in this case, whereas the L2 divergence does not have the property, right? But then in exchange, we are paying a penalty. What is the derivative of the KL divergence at the correct answer, at d equals 0? Is the derivative 0? What's the slope? For the blue curve?
Non-zero.
It's non-zero. The blue curve has a slope of 1, right? At d equals 0. Similarly, if the desired output is 1, the blue curve has a slope of minus 1 at d equals 0. So what does this tell you? Is checking whether the derivative is 0 a good thing to be doing to find out if I'm at a minimum? Yes or no? Can I hear that together, everybody?
No.
Thank you, right? So which is why when we were looking at gradient descent, we were looking at whether the function was changing or not, but you're not actually testing the derivative. Because as you can see over here, in fact, for the KL divergence, the derivative is going to be a very hefty 1 at the optimum, right? Everybody with me? So note that when y equals d, the derivative is not 0, even though the divergence is 0, right? If I go to the multi-class classification problem, we're going to have the same kind of characteristic. We're going to use the Kullback-Leibler divergence also, which is defined. So the reason we use the Kullback-Leibler divergence is that when you're wrong, it tells you are infinitely wrong, which is a very nice behavior. That's what you want in a probabilistic setting, right? So, and there's another reason, we'll see that in a few classes. So the KL divergence, again, the d can be thought of as a probability vector. The y is a probability vector. The d is just an extreme probability vector, 1 and all zeros, right? And so the KL divergence between the two is defined as the sum over all classes of the desired output for the class times log of d over y, which is summation d log d minus summation d log y. Now, if I'm using a one-hot representation, what is this first term going to be? For all the non-target classes, d is 0, right? For the target class, log d is 0 because d is 1. So in the first term, either the d is 0 or log d is 0, the first term goes away, right? So you're only left, so although I've given you a very ugly looking formula over here, when you begin simplifying things, it becomes very simple. Now what about the second term? For the non-target classes, d is 0. So they go away. The only thing that remains is the target class, right? And therefore, the KL divergence just reduces to the negative of the log of the probability assigned to the target class, which is very nice, right? It's a very simple formula. Minus of log y of the target class is the KL divergence between the desired output and the actual output of the network. Everybody with me? Is that making sense to everyone? All right. And here's the nice thing. If I'm looking at the derivative of the KL divergence with respect to the output of the network, do the probabilities of the non-target classes figure over here? So when I'm looking at the KL divergence, guys, yes or no? Do the probabilities of the non-target classes figure? Yes or no? Can I hear that loud? Right? Because it's not there in the formula. What is the formula? It's just minus log y for the target class, right? So what this means is that you're going to try to increase the probability of the target class, and just as a secondary effect, because you're increasing this, the rest of them must go down, right? If you look at the derivative of the divergence, again, it's going to be 0 for all the non-target classes and minus 1 over yc for the target class. And again, look at this. Is the partial derivative of the divergence with respect to the probability assigned to the target class positive or negative? Look at the formula. Is the derivative positive or negative? The formula is minus 1 over yc, right? So is it positive or negative? Negative? Right. So does that make sense, Junior? Does that make sense? Why does it make sense? So Arya, can you tell me? Should I be increasing the probability of the target class or decreasing it to reduce the error? Are you sure you must be increasing it? You better be sure, right? Okay, can somebody help her? Laura, can you help her? Should you be increasing the probability of the target class or decreasing it? Increasing it. Why? You want to choose the target class. You want to be certain that it's the target class, right? And so in that case, what will the derivative of the error be? Increasing the probability of the target class decreases the error. What's the derivative going to be, positive or negative? Negative, right? What is the formula telling you? Minus 1 over yc. Is that going to be positive or negative? Negative, right? And so here's the thing. It has this very nice behavior. When y is 0, it's a very large slope. It says this is going to change very fast. As y gets closer to 1, the slope becomes smaller and smaller. And so it has this nice property that the derivative itself gets closer, smaller, closer to the minimum, right? So everybody with me? Questions, guys? Any questions? No? Okay. So let's move on. Again, note that when y equals d, the derivative is not 0, right? 1 over yc. When the target output and the actual output are the same, yc is going to be 1. Minus 1 over 1, the gradient is going to be all zeros with one component being minus 1. So checking whether the derivative is 0 is not a useful thing to be doing, right? And now, one last point before we end the class, and there will be a final poll for those who want to stay. Now, here's how the softmax is computed. So before you compute the softmax, you first compute an affine value z, and the z is put through a softmax, correct? And then that gives you a bunch of probabilities, and then you have a desired output. You're computing the KL divergence between the two. The plot that we just saw, the equations that we just saw, gave you the derivative of, what is happening? So it gave you the derivative of the KL divergence with respect to y, the derivative of the KL divergence with respect to the output of the network. But if you take a step back, someone posted this on Piazza, and I'll give you the proof. It is very trivial. If you take a step back and compute the derivative of the KL divergence out here, with respect to the affine value z, not with respect to the output of the softmax, but with respect to the input, the affine term that's input to the softmax. Guess what? That also reduces to just the error, y minus d. The error between the output of the network and the desired output of the network, which means you don't even have to work through the math. You don't have to write code for it. You just say y minus d and you're done, right? So it's very simple. So regardless of whether you're actually using the L2 error in the case of predicting real values, when you're predicting real values, you won't have a softmax activation. In fact, typically you have no activation at all. So in that case, the derivative of the L2 divergence with respect to the affine value is the error between the output of the network and the desired output. In the case of classification, when I compute the derivative of the KL divergence with respect to the affine term, that too ends up simply being the error between the output of the network and the desired output of the network. So both of these losses have this very nice property. Across both classification and regression, they give you the same kind of derivative, which is an error. So all terms have been defined. I have also defined the divergence function. This is a final poll. You have a minute, and then we're done. Any questions? Something's off. Okay, let's just stop this because it's at 9:20. But does anybody want to answer this question? The gradient of the loss will always be 0 or close to 0 at the minimum. True or false?
False.
The gradient is not going to be 0, right? The gradient of the loss may be 0 or close to a 0, maybe 0 or close to 0 at a minimum. True or false? True, it could be, right? L2. It may have a large magnitude at a minimum, true or false?
True.
True, we saw this for the KL, right? But if the gradient is not 0 at a minimum, it must be a local minimum, true or false?
False.
That's a nonsense statement, right? So, perfect. You guys have nailed everything. Thank you. Those are the answers. So the story so far, neural networks are universal approximators. Networks are trained to approximate functions by adjusting their parameters to minimize the average divergence between their actual and desired outputs. And to train them, several things must be defined. The network, the manner in which the inputs and outputs are presented. They're typically as vectors of numeric values or as one-hot vectors. And a divergence function that computes the error between the actual and desired outputs, which is typically L2 for regression and KL divergence for classification. We will continue with this in the next class. Thank you very much.